Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on chapter 6. Let's go ahead and get started with problem number 1. Problem number 1 says a reaction is found to stop just before all reactants are converted to products. Which of the following could be true about this reaction? Now, just some background information. Remember the difference between irreversible reactions and reversible reactions. In irreversible reactions, these reactions proceed in one direction only, from reactants to products, and they do not go backwards. Once products are formed, they do not revert to reactants, and they usually go to completion. Reversible reactions, these are reactions that can proceed in both directions, meaning reactants can form products and products can revert back to reactants. Now, for reversible reactions, equilibrium is reached when the rate of the forward reaction equals the rate of the reverse reaction. And so at equilibrium, the concentrations of reactants and products remain constant, though they're not necessarily equal. They just remain constant. Keeping that in mind, let's go ahead and read our answer choices. Answer choice A says that this reaction is irreversible and the forward rate is greater than the reverse rate. Now, in an irreversible reaction, the reverse rate is essentially 0 because products can't go back to reactants. They cannot revert to reactants. If the forward rate is greater than 0, then the reactants should continue converting to products until all of the reactants are used up and we've formed products. This doesn't make any sense. This does not explain why the reaction stops before all of the reactants are converted. And so that means answer choice A is incorrect. Answer choice B says the reaction is irreversible and the reverse rate is too large for products to form. Again, if a reaction is irreversible, by definition, the reverse rate should be 0 or negligible. Having a large reverse rate contradicts the concept of an irreversible reaction. So answer choice B is also incorrect. Answer choice C says that the reaction is reversible and the forward rate is equal to the reverse rate. So in a reversible reaction, when the forward rate equals the reverse rate, the system reaches equilibrium. At equilibrium, the reaction does not proceed in either direction in a net sense, meaning that the concentration of reactants and products remain constant. This fits the description of the reaction stopping before all of the reactants are converted. So answer choice C makes a lot of sense. It could be the correct answer, but let's work through D as well. D says the reaction is reversible and the reverse rate is greater than the forward rate. Now, if the reverse rate is greater than the forward rate, then the reaction would favor the formation of reactants over products. This would lead to a situation where reactants are continually formed from products, preventing complete conversion of reactants to products. This is incorrect in the context of the reaction stopping before all of the reactants are converted because it implies a net reverse reaction dominance rather than stopping. And so answer choice D is also incorrect. The correct answer for 1 is going to be C. All right, and so in summary, to get to the point, this scenario likely describes a situation in which a reaction has reached equilibrium very far to the right with high product concentration and low reactant concentration. And this reaction must be reversible because the reaction did not proceed all the way to the right. Any reaction in equilibrium then has an equal forward and reverse rate of reaction. So again, the answer to problem 1 is C. Let's go ahead and move into problem 2. Problem 2 says, what is the equilibrium expression for this reaction? Now, looking at the reaction, remember that our equilibrium expression for a generic reaction that has A moles of reactant A and B moles of reactant B giving us C moles of product C and D moles of product D, follows the following rules. We have the concentration of our products raised to their respective stoichiometric coefficients over the concentration of our reactants raised to their respective stoichiometric coefficients. So just as a friendly reminder, this is how we can write our equilibrium expression for a generic reaction. There are a couple of important notes to keep in mind. In equilibrium expressions, the concentrations of pure solids and liquids are not included because their concentrations do not change. Only the concentrations of aqueous and gaseous species are included in the equilibrium expression. So if we're looking at this reaction right here, we notice that the reactant is a solid. It will not be included in our equilibrium expression. It is also the only reactant, so actually our equilibrium expression will not have a denominator. So if we're going to write the equilibrium expression for this reaction, it's going to be our reactants, which is copper ion, raised to its stoichiometric coefficient, so raised to the power of 2, multiplied by our sulfate ion, raised to its stoichiometric coefficient. It only has a coefficient of 1, so it's just raised to the power of 1. Now, the correct answer here is going to be answer choice D because that best aligns with what we just wrote. All right, again, remember, please, the concentrations of pure solids and liquids are not included in our equilibrium expression. And with that, we've solved problem 2 as well. 2 is D. Let's do problem 3 now. Problem 3 reads, carbonated beverages are produced by dissolving carbon dioxide in water to produce carbonic acid, and we're given the following reaction for that. Now, when a bottle containing carbonated water is opened, the taste of the beverage gradually changes as the carbonation is lost. Which of the following statements best explains this phenomena? All right, let's read our answer choices and then work through this. Answer choice A says the change in pressure and volume causes the reaction to shift to the left, thereby decreasing the amount of aqueous carbonic acid. B says the change in pressure and volume causes the reaction to shift to the right, thereby decreasing the amount of gaseous carbon dioxide. C says carbonic acid reacts with environmental oxygen and nitrogen, and D says carbon dioxide reacts with environmental oxygen and nitrogen. Now, this problem requires us to remember Le Chatelier's principle, which states that if a dynamic equilibrium is disturbed by changing the conditions, the system responds to counteract the change and restore a new equilibrium. Now, for this carbonation in beverages, we have carbonated beverages that contain dissolved carbon dioxide, which reacts with water to form carbonic acid. Now, when the bottle is opened, what happens? Well, what happens is that the pressure inside the bottle decreases, causing carbon dioxide gas to escape. Now, when you open that can, you're decreasing the pressure of the bottle. You're doing this because you're increasing the volume. The container is no longer contained in just the bottle. When you open it, now the volume increases because it also involves the outside environment. So what you're doing is you're decreasing pressure by increasing volume. And that means that we have to remember our rules for decrease in pressure, increase in volume. For this scenario, the system will shift in the direction that produces more moles of gas. So let's go back and look at our reaction. Our reactant side has 2 moles of gas, and our product side has 1 mole of gas. Since we're decreasing pressure, increasing volume, we favor the side that produces more moles of gas, which means we favor the reactant side. That means our reaction shifts to the left. That aligns with answer choice A, where it says that the change in pressure and volume causes the reaction to shift to the left, thereby decreasing the amount of aqueous carbonic acid. The correct answer for 3 is going to be A. Now let me just rephrase this and summarize it. Carbon dioxide gas evolves and it leaves the bottle. That decreases the total pressure of the reactants. And Le Chatelier's principle explains that a decrease in pressure shifts the equilibrium to increase the number of moles of gas present. And for this particular reaction, the reaction will shift to the left. And that means we're going to decrease the amount of carbonic acid and increase the amount of carbon dioxide and water. Now, answer choices C and D are really just throwaways. Oxygen and nitrogen are not highly reactive and are unlikely to combine spontaneously with carbon dioxide or carbonic acid. So again, the correct answer for problem 3 is A. Problem 4 asks, which of the following best describes how to favor the production of the kinetic product over the thermodynamic product? Now, this allows us to recall kinetic versus thermodynamic control. Remember, for kinetic control, the product formed under kinetic control is the one that forms the fastest. This product is favored by lower activation energy, and it's usually formed at lower temperatures and shorter reaction times. It is not necessarily the most stable product, but it forms quickly. This is in contrast to the thermodynamic control. The product formed under thermodynamic control is the most stable product. This product is favored by higher temperatures and longer reaction times, allowing the system to reach equilibrium and form the most stable product. Now, to answer this problem, we're looking for conditions that will favor the kinetic product, and that is going to be low temperatures and shorter reaction times. That aligns the best with answer choice B. So for problem 4, the answer is B. Wonderful. Let's move on to problem 5. Problem 5 says if the equilibrium constant is greater than 1, blank. Our answer choices are A, the equilibrium mixture will favor products over reactants. B, the equilibrium mixture will favor reactants over products. C, the equilibrium concentrations of reactants and products are equal. And D, the reaction is essentially irreversible. Now, the equilibrium constant is a measure of the ratio of the concentrations of products to reactants at equilibrium for a given reaction. And it's given by the following expression, where the concentrations are raised to the power of their respective coefficients in the balanced chemical equation. Now what we want to do is go over what it means when this equilibrium constant is greater than 1, less than 1, or equal to 1. When the equilibrium constant is greater than 1, this indicates that at equilibrium, the concentration of products is much higher than the concentration of reactants. In other words, the reaction heavily favors the formation of products. Now, when the equilibrium constant is less than 1, this indicates that at equilibrium, the concentration of reactants is much greater than the concentration of products. And here, in other words, the reaction heavily favors the formation of reactants. When the equilibrium constant is approximately 1, this means that the concentrations of reactants and products are comparable at equilibrium. Now, this problem is specifically asking us what is true when the equilibrium constant is greater than 1, and we just discussed that the concentration of products is much higher than that of the reactants, and the reaction heavily favors the formation of products. This aligns with answer choice A. So the correct answer for problem 5 is A. Let's read problem 6. It says acetic acid dissociates in solution according to the following equation. So this is acetic acid. This is what it dissociates into. If sodium acetate, which is this species right here, is added to a solution of acetic acid in excess water, which of the following effects would be observed? A says decreased pH, B says increased pH, C says decreased pKa, D says increased pKa. So really quickly, the answer choices we have here are on topics that we're going to cover in the acid-base chapter, but they're important for us to understand briefly here to answer the problem. So I'm going to go over the concepts really quickly. pH is the measure of the hydrogen ion concentration in the solution, and it's calculated as the negative log value of that hydrogen ion concentration. Now, with negative logs of something, if your hydrogen ion concentration is decreasing, the negative log of that is going to give us a consequence of an increased pH, and vice versa. If you have an increased hydrogen ion concentration, you're going to have decreased pH. And that's because the pH scale is on a scale of 0 to 14. 7 is neutral. Anything below 7 is acidic. All right. Anything greater than 7 is basic. So just some preliminary information here. Now, as for pKa, Ka is just the acid dissociation constant, all right? It's the equilibrium constant for acid dissociation. Whenever there's a P in front of something like you see with pH, this just means that we're taking the negative log value of that Ka value, of that acid dissociation constant. Now, something to note about pKa is that it's an intrinsic property. All right, so for acetic acid, the pKa is an intrinsic property of the acetic acid molecule itself, and it's defined under standard conditions. All right, adding sodium acetate to this solution, it's not going to affect the pKa value. It will affect the pH, however. So that fact alone allows us to eliminate answer choices C and D. Now, let's work through this problem. We're adding in sodium acetate. That's this molecule right here. So what we're doing is we're adding more product. Le Chatelier's principle says that when you are adding more product, that we will form more reactants to reestablish equilibrium. So in other words, Le Chatelier's principle predicts how the equilibrium will shift when a change is imposed on a system at equilibrium, and adding more acetate ions will shift our equilibrium to the left. All right? If we're adding more product to reestablish equilibrium, we favor the formation of reactants. Now, the consequence of this is we're going to reduce the concentration of hydrogen plus ions to maintain equilibrium. And that fact is really important because it's going to help us determine if the correct answer is A or B. If we are decreasing the number of free hydrogen ions, the pH is determined by that free hydrogen ion concentration. So a decrease in the number of hydrogen ions is going to result in an increase in pH. And so the correct answer here is going to be B. All right, let me summarize that. Let's put all of this together. Adding sodium acetate increases the number of acetate ions present. And according to Le Chatelier's principle, this change will push the reaction to the left. That will result in a decrease in the number of free hydrogen ions. Now, because pH is determined by the hydrogen ion concentration, a decrease in the number of free protons or free hydrogens will increase the pH. Now, an acid's Ka value, which is the equilibrium constant for acid dissociation, that's going to remain constant under given temperature and pressure, hence why we eliminated C and D off the bat. The correct answer for 6 is B. Let's go ahead and move on. Now, the next two questions are going to refer to this reaction right here. Let's go ahead and read problem 7. Problem 7 says, which of the following would increase the formation of product? A says decreasing the volume of the container. B says decreasing the pressure of the container. C says increasing the volume of the container. And D says decreasing the volume of the container while maintaining a constant pressure. Now, this problem relates to Le Chatelier's principle, which states that if a system at equilibrium is subjected to a change in concentration, pressure, or temperature, the system will adjust to counteract the change and re-establish equilibrium. Now, the answer choices relate to changes in pressure and volume, so let's remind ourselves what a change in pressure and volume does to our system. If we were to increase pressure and thereby decrease volume, because those things are related, all right, increase pressure, decrease volume, the system will shift in the direction that produces fewer moles of gas. All right, so that's for increase in pressure, decrease in volume. What about decreasing pressure, which would result in an increase in volume? This will result in the system shifting in the direction that produces more moles of gas. And so if we are trying to increase the formation of product, this is our product, which scenario do we prefer? This requires us to look at how many moles we have on the reactant side versus the product side. On the reactant side, we have 2 moles. On the product side, we have 1 mole. If we are trying to increase the formation of products, we are favoring the direction towards fewer moles of gas. That means that we want to increase pressure, decrease volume. The correct answer is going to be A, decreasing the volume of the container. Now, answer choice D also says decreasing the volume of the container, but it says while maintaining a constant pressure. D would not disturb the equilibrium. The significance of decreasing the volume of the container in most equilibria is that there is an increase in pressure. In this case, though, they're saying that the pressure remains constant. All right, and that means that answer choice D is not the correct answer. 7 is A. Let's read 8 now. 8 says if the reaction were exothermic, remember that exothermic means that delta H is less than 0 and heat can be considered part of the products. What effect would decreasing the temperature have on the equilibrium? A says that the forward and the reverse reaction rate both increase. B says that the forward reaction rate decreases while the reverse reaction rate increases. C says that the forward reaction rate increases while the reverse reaction rate decreases. And D says that both forward and reverse reaction rate decrease. So again, if we have an exothermic reaction, we have heat as the product. If we are decreasing temperature, we're essentially removing heat, which means that we are removing product. If we're removing product to reestablish equilibrium, our reaction is going to favor the formation of products. If we're favoring the formation of products, then our forward reaction rate should increase while our reverse reaction rate should decrease. And that best aligns with answer choice C. So 8 is C. Next up, problem 9. Problem 9 asks which of the following actions does not affect the equilibrium position of a reaction. A says adding or removing heat. B says adding or removing catalyst. C says increasing or decreasing concentrations of reactants. And D says increasing or decreasing volumes of reactants. Now, the equilibrium position of a reaction is the relative concentrations of reactants and products at equilibrium. And this position can be shifted by changes in concentration, pressure or volume, and temperature according to Le Chatelier's principle. Le Chatelier's principle states that if a dynamic equilibrium is disturbed by changing the conditions, then the position of the equilibrium will shift to counteract the change. Now, with that being said, answer choice A, adding or subtracting heat, this would shift the equilibrium based on the enthalpy change of the reaction. So A is true. This would affect the equilibrium position of a reaction, but we're looking for something that doesn't. So we can eliminate this answer choice. Now C says increasing or decreasing concentrations of reactants. Increasing reactant concentrations would shift the equilibrium in the direction of the product. And the opposite would occur if reactant concentrations were decreased. And we can say the same thing about products as well. In short, changing the concentration of reactants or products will shift the equilibrium to oppose the change. So C is not our answer either. D says increasing or decreasing volumes of reactants. Now, changing the volume of a reactant would affect any reaction with a gaseous reactant or product. So yes, this would also affect the equilibrium position of a reaction. So we can go ahead and eliminate that answer choice as well. What we're left with is answer choice B, adding or removing a catalyst. Now, adding or removing a catalyst would change the reaction rates, but it would not affect or change where the equilibrium lies. And so for our question, which of the actions does not affect the equilibrium position of a reaction, the correct answer is going to be B. 10 says in a sealed 1 liter container, 1 mole of nitrogen gas reacts with 3 moles of hydrogen gas to form 0.05 moles of ammonia at equilibrium. Which of the following is closest to the equilibrium constant of the reaction? So the first thing that you notice here is you're not given the balanced chemical equation. So that is the first thing that you want to do. We're told that we have nitrogen gas reacts with hydrogen gas to give us ammonia. And we want to make sure that this is balanced. And you'll notice really quickly that it isn't, right? We have 2 nitrogens on the reactant side, but only 1 on the product side. So let's add a coefficient of 2 right here. Now we have balanced nitrogens on both sides. What about the hydrogen? We have 6 hydrogens on the product side, but only 2 on the reactant side. So we're going to go ahead and add a coefficient of 3 right here to make sure that everything is balanced now. In addition, let's go ahead and just write the structure of our equilibrium constant expression. This is going to equal the concentration of the products raised to their stoichiometric coefficients over the concentration of the reactants raised to their respective stoichiometric coefficients as well. So here is our expression. And now what we want to do is fill out our ICE table so that we have things to substitute back into this expression and hopefully calculate our equilibrium constant. So let's start off with what we know. We're given the number of moles for each species and the volume of the container, so we can easily calculate our initial concentrations. We have 1 mole of nitrogen gas, and we're going to do 1 mole divided by 1 liter to give us 1 molarity for our nitrogen concentration. For hydrogen, we have 3 moles of hydrogen gas divided by 1 liter. Moles divided by liter gives us molarity. This is going to give us 3 molar for hydrogen gas. And then ammonia, we have 0.05 moles of ammonia, and we're going to divide that by 1 liter to get the molarity, which is going to be 0.05. So those are our initial concentrations for our reaction. Now, as this reaction proceeds, we're going to consume reactants to form products, and we're going to denote our change as X. And we want to make sure that the coefficient that's associated with that X variable demonstrates the ratios between our species. So we're going to have nitrogen being consumed minus X and hydrogen gas being consumed minus 3X, because there is a 1:3 ratio between nitrogen and hydrogen gas, and we're going to consume those species to form ammonia plus 2X, because there is a 1:3 to 2 ratio between nitrogen, hydrogen gas, and ammonia. Okay, so that is our change. Now our final category is equilibrium, and equilibrium is just initial plus or minus the change. So for nitrogen gas, it's going to be 1 minus X. For hydrogen gas, it's going to be 3 minus 3X. And for ammonia, it's going to be 0.05 plus 2X. Wonderful. Now we can go ahead and plug things back into our equilibrium constant expression. So let's go ahead and do that and then begin to think how we can simplify the math for this problem. So we're going to have ammonia here at the top, 0.05 plus 2x, that's in the numerator for ammonia. And then in the denominator, we have 1 minus x and 3 minus 3x. Now here, we're going to take advantage of a really important simplification. All right, we can simplify our calculations by making the assumption that the change in concentration of a reactant and product X is negligible compared to the initial concentrations. If you remember, this rule is usually known as the 5% approximation rule, and it serves as a guideline that helps us determine when it's reasonable to make some simplifications to calculate this a little bit easier, especially for the MCAT when you don't have a calculator. Now, this rule states that if the change in concentration X is less than 5% of the initial concentration, then X is negligible. And we're going to assume this because for the MCAT, this is usually a safe bet since you're not allowed to use calculators. And without a calculator, you wouldn't be able to solve this problem as is because it requires the use of a quadratic formula. And that is outside the scope of the exam. So what that means with our 5% approximation rule is we're saying that X is so negligible that we can essentially omit it from our calculation. And that makes things a lot easier. Do not forget your stoichiometric coefficients here like I initially did. So now we have a lot easier of a math problem to solve. Now we have Kc is equal to 0.05 squared over 1 to the 1 power, 3 to the 3rd power. And this is easy. So what's 5 squared? That's 25. But notice that there's 2 decimals here, and you're multiplying 0.05 by 0.05. So yes, you have the 25 from the 5 times 5, but you have to accommodate for the 2 zeros as well. So what that's going to give us is 0.0025. And then in the denominator, 1 to the 1 power is just 1, and 3 to the 3 cubed is 3 times 3, which is 9, times 3, which is 27. All right, so then we have something that looks like this. Now, what we can do to make this final calculation a little bit easier is I'm going to write the numerator in scientific notation. In proper scientific notation, I'm going to write 25 times 10 to the minus 4th power. And the reason why I want to do this is because I'm going to approximate the denominator from 27 to 25. And look at that. That makes this calculation really easy. This is about 1 times 10 to the minus 4. Or in other words, 0.0001. And that aligns with one of our answer choices. It aligns with answer choice A. So 10 is going to be A. Beautiful. Look at that. We did the math together. It's not too bad. Don't be nervous making approximations here and there, right? Usually the answers are far off enough that making little bits of approximations is not going to deviate you away from the answer too much. Notice how these answer choices, they're different by orders of magnitude, right? So making an assumption like 27, approximating it to 25 is not going to hurt your answer. Wonderful. Let's move on to problem 11. 11 says increasing temperature can alter the equilibrium constant of a reaction. Why might increasing the temperature indefinitely be unfavorable for changing reaction conditions? A says that the equilibrium constant has a definite limit that cannot be surpassed. Now, this implies reactions have limits, which is true. However, that does not make increasing temperature unfavorable. Let's read B. B says the products or reactants can decompose at high temperature. This is a very valid concern. At very high temperatures, reactants or products might decompose, leading to the breakdown of the desired equilibrium and the formation of unwanted byproducts. This is a very good reason why raising the temperature indefinitely might be unfavorable for a reaction. Let's keep that answer choice in mind. C says increasing temperature would decrease pressure, which may or may not alter reaction conditions. Now, increasing temperature typically increases pressure in a closed system, not decreases it. So this statement is just based on incorrect assumptions. So this is not a valid answer choice. D says if a reaction is irreversible, its equilibrium constant will resist changes in temperature. Now, irreversible reactions do not have an equilibrium constant in the same sense as reversible reactions. And so the statement is really not relevant to the context of equilibrium shifts due to temperature changes. And so D is incorrect because it refers to properties of irreversible reactions, which would not be involved in an equilibrium between products and reactants. And so going through the answer choices, the one that makes the most sense why increasing the temperature indefinitely is unfavorable is answer choice B. Let's read 12. 12 says, how does the change in free energy compare between the kinetic and thermodynamic product? So as a reminder, the kinetic product is the product that forms the fastest. It typically has a lower activation energy, but may not be the most stable product. The thermodynamic product is the product that is the most stable. It typically has a higher activation energy and it forms more slowly, but it is more stable than the kinetic product. Now we know that the change in Gibbs free energy determines the stability of the product. A more negative delta G indicates a more stable product. And so the more stable the product, the lower or more negative the free energy. Let's go ahead and start reading these answer choices together so that we can determine what the correct answer is. A says the free energy change for the kinetic product is greater since it is less stable. B says the free energy change for the kinetic product is greater since it is more stable. C says that the free energy change for the thermodynamic product is greater since it is less stable. And D says that the free energy change for the thermodynamic product is greater since it is more stable. Now again, the thermodynamic product is more stable than the kinetic product, making the thermodynamic product lower in energy. Now because the energy of the product is lower, the change in free energy is greater for the thermodynamic product compared to the kinetic product. And so the correct answer for 12 here is going to be D. The free energy change for the thermodynamic product is greater since it is more stable. Beautiful. 13. Problem 13 reads, compound A has a Ka, this is the equilibrium constant of acid dissociation, of approximately 10 to the minus 4. Which of the following compounds is most likely to react with a solution of compound A? Now, I want to preface this question by saying that it requires a little bit of background knowledge on acid-base reactions, just like problem 6 did. If you haven't taken Gen Chem before and you don't have that background knowledge, or you've taken Gen Chem years ago and you don't feel confident in your acid-base knowledge, that is totally okay. We're going to cover acids and bases in its whole own chapter in this playlist, but if you want for now to skip these problems and come back to them later after that video is released, that is totally fine. Nevertheless, I'm going to try to provide some background information to get us going and solving this problem together. So this acid dissociation constant, Ka, is a measure of the strength of an acid in solution. It represents the equilibrium concentration of the acid dissociating into hydrogen ions and conjugate base. So it looks something like this. Ha, which is our acid, it dissociates into hydrogen ions plus its conjugate base. Now, a Ka of 10 to the minus 4 indicates that compound A is a acid. Specifically, it is a weak acid because strong acids typically have much higher Ka values. Now, in acid-base reactions, acids are going to react with bases to form water and salt. Therefore, identifying a compound likely to react with compound A involves us looking for a base. So we're going to go through our answer choices and talk about each one and try to figure out which one is a weak base that's going to react with our weak acid. Now, this first option A, this is nitric acid. This is a strong acid. Strong acids do not typically react with weak acids in simple acid-base reactions. So this is not the answer choice that we're looking for. The next option is nitrogen dioxide. Now, this is a gas and it's not typically considered a base in aqueous reactions. It doesn't readily react with weak acids in the context provided. So this answer choice is also incorrect. C is ammonia. Now, ammonia is a weak base, and weak bases react with weak acids to form their conjugate acids and bases. Ammonia is likely to react with compound A, and it is the correct answer. So 13 is C. Now, the last option, this is dinitrogen pentoxide. This is an acidic oxide that forms nitric acid in water. It's not a base and it doesn't react with weak acids in the context provided as well. So it's also not the correct answer. With that, again, the correct answer for 13 is C. Let's move on to 14. Problem 14 says, consider the following two reactions. Here we have reaction 1. And here we have reaction 2, and quickly you notice that they are the reverse of each other. So reaction 1 is 3A plus 2B, gives us 3C plus 4D, and reaction 2 is 4D plus 3C, gives us 3A plus 2B. Now, if the equilibrium constant for reaction 1 is 0.1, what is the equilibrium constant for reaction 2? Since reaction 2 is the reverse of reaction 1, this means that the equilibrium constant for reaction 2 is just the inverse of the equilibrium constant of reaction 1. So to figure out the KEQ for reaction 2, we just do the inverse of the equilibrium constant for reaction 1. So it's going to be 1 over 0.1, and that is equal to 10. And so the correct answer for 14 is C. Let's go ahead and do our last and final question. Problem 15 says, which of the following statements best describes the effect of lowering the temperature of the following reaction? Now, here we have A plus B gives us C plus D, and we have the delta H, we have the enthalpy. The enthalpy is minus 1.12 kilojoules per mole. This negative delta H value indicates that what we have is an exothermic reaction. So we have an exothermic reaction and we're decreasing temperature. Now, for exothermic reactions, you can consider heat as the product. If we are lowering the temperature, that means that we are essentially removing heat. All right, that means we're removing a product. What happens when we remove a product? How does this reaction reestablish equilibrium? By favoring the formation of more products to compensate for the fact that we are removing product. And that's going to result in an increase in the concentration for product C and D. And that means the correct answer here is going to be A. And with that, we've answered our last and final problem. I hope that this video was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.